Let's finish up this section and work on a couple of examples. We just learned that there is an EMF induced when a conductor is moving through an external field. The equation we came up is as follows. I usually write it as delta V equals BLV. Let's take a look at example number 4. So this happens in real life while you're driving. Your metal car has a lot of metal, that's a conductor, and when it's moving through the external field of the earth, then there is an EMF induced in your car. So if you're driving within the Earth's magnetic field here, you're going at 33.5 meters per second. The magnetic field has a vertical component downward, and it gives you the width and the length of your car. What's the induced EMF, and is it positive on the driver's or the passenger side? So we know that when there's a bar that is moving perpendicularly to a field, there will be an EMF induced. What's a little bit tricky here is, what do we use? Do we use the length or the width of the car? The equation that we just came up with said that the EMF induced is going to be BLV. And that makes us think that L stands for length, so that we need the length of the car. But we really need to visualize what's happening to figure it out. So what I've drawn here is just a metal conductor, and it's like the car, so this side here is going into the page. This is the width of the car, and this is the length of the car. So let's consider what happens to a positive charge that's right here. There are positive and negative charges everywhere. So if a positive charge is here, and use right-hand rule number 3 to find the direction of the force on that charge, you put your fingers in the direction of V, which is into the page, and then you have to fold in the direction of B. So that means that you should have your fingers pointed at the screen. And again, it's hard to draw that because that looks like my fingers are pointed up here. But if you see the knuckles and you've got the wrist here, again, very hard to draw, but those fingers are pointed into the screen here. That way I can fold them down into the direction of the magnetic field, and my thumb is the force pointing to the left. So all the positive charges experience a force to the left. This means that all of the negative charges will experience a force to the right. So all the negative charges will accumulate on the right side. All the positive charges experience a force to the left will accumulate on the left side. So what we see here is that there's a potential difference created between the left end and the right end. So this L here is the distance between those 2 points where that potential difference is occurring. So that's what we actually want. So this L here is actually the width of the car. We don't really care about the length of the car. So we're going to use the 1.5 meters here for the width of the car, which we're calling L from this equation. And now we can plug and chug the other variables. Our magnetic field that's going downwards is 5 times 10 to the negative 5 teslas. And then our speed is 33.5. meters per second. So plug in the B, the V, and the L that we have right here, the 1.5, plug it into this equation, and we're going to get 2.51 millivolts, or times 10 to the negative 3 volts. So in real life, you do have a potential difference that is produced. Also, if you're in an airplane, right? If it's airplanes moving a little bit faster than you are, then you have more potential difference created or induced, but it's still a very small number, so it's not very, very significant. Let's go ahead and look at one more example. Example 5 here. So what we have here is we have a conducting bar, right? This is a piece of metal over here, It's moving to the right. There's an external field that is going into the page. So it's into the page on this side as well. The picture doesn't show it, but it extends into the page everywhere. And the difference between this and the previous example is that this bar is connected to a circuit here. So if we have an EMF induced in this bar because it's moving in an external field, now that the bar is connected to the circuit, there will be a current in the circuit. So the first question is, what is the direction of the induced current? There are two ways that we can solve this. One way is we can go ahead and use the right-hand rule and see, well, what is the direction of the magnetic force on the charges in this bar? And it's not this. We can ignore this for now. We don't really need this right now. But if you just consider a positive charge in this bar here, it's moving to the right. So you point your fingers to the right. Your thumb is going to point up so that you can fold your fingers here into the page, into the direction of the magnetic field. Your thumb is the force pointing up. So all of the positive charges will accumulate over here due to the magnetic force. All the negative charges will be over here. So you can see this potential difference induced. You can think of it like a battery, this being the positive terminal of the battery and this being the negative terminal of the battery. In that case, we know that the current always flows away from the positive terminal. That means the induced current is going to be counterclockwise. You can see it's going to the left here, down, and to the right, and up. That's counterclockwise. Now, another way that we could solve this is by considering Lenz's law. When we have this conductor here attached to this circuit, it's creating a loop. As the bar is moving to the right, the loop is getting bigger. That means that the flux through this loop here, this loop right here, the flux through it is going to change. So we can use Lenz's law to figure out the direction of the induced current. If you remember the steps that we talked about in our Lenz's law video, the first step is which way is the field? Well, the external field here is going into the page. And then you ask yourself, is the flux increasing or decreasing? Well, the area of the loop is getting bigger as the bar moves to the right. So that means that the flux is increasing. And then the third thing is if the flux is increasing, then the induced field is going to be in the opposite direction as the original. So induced field is going to be out of the page. So now we have to figure out, well, what's the direction of the induced current in this loop that will produce an induced magnetic field out of the page? And this is where you use right-hand rule number 2. You curl your fingers in such a way, which is going to be this way. Getting a lot of practice drawing my fingers here. It's very hard to draw. This looks pretty bad. But what you see is my thumb here and my fingers curling this way and my thumb pointing towards me because I want the field, which is the thumb, to be out of the page, so the fingers have to curl this way, which is counterclockwise. So I just made a fist here. So that's another way to see that the induced current is going to be counterclockwise so that it produces a field out of the page to oppose the fact that the magnetic flux was increasing and that the field was into the page. Let's look at the second part of this example. It says, what is the magnitude of the current in terms of the given? So we don't have any numbers here, but we know that the EMF that is induced is BLV. That's the EMF induced across this bar here. And we also know that if there's a current in this circuit here, we can use Ohm's law that says the current is going to be the delta V over R, the resistance. And the delta V, or the induced EMF, is the magnetic field, the length, and the speed divided by R. So that's really all that we had to do for this part, is just show that yes, indeed, there is a current induced in this loop. Now the last thing I want to talk about is, okay, well, what in the world are these arrows here? Because we saw that the magnetic force was upward, so why is this showing an arrow to the left here? So what we're saying is, okay, we now have a current induced in this bar. Current is going counterclockwise, so it's going up through the bar. So now what we're doing is we're using right-hand rule number 3 again to see, okay, well, on this bar, what is the magnetic force on this bar? Because you have a current going through this bar, a current going up. And the right-hand rule, number 3 again, says you put your fingers in the direction of the current, you put them up, and I'm going to put them up this way so that my thumb can point to the left and my fingers can again fold into the page here. So you should have your fingers folding away from you. Your thumb is pointing to the left. That's the direction of the magnetic force. Because your fingers up is the current, you fold into the page for the magnetic field. The thumb is the magnetic force. So that's what this is showing, that on this current carrying conductor here, there's a magnetic force to the left. So what this is saying is that if you are trying to move a conductor to the right here, this magnetic force will kind of serve as a braking force. It will oppose that motion. So you'll actually need an applied force to counteract this magnetic force if you want to keep moving this bar to the right. So this is known as a braking force. That's all for this video. I hope that you learned a little bit, and be sure to practice the your turn question in the other video.